So if there must be a stronger field inside this resistive region to maintain the same current in and out of that region, well, what creates that stronger field? What changes the value of the field? We've got to find the charges that are responsible for this. So where are those charges located? Now, we previously dismissed the possibility of excess charge anywhere inside the wire using a Gauss's law or a Gaussian bag-based argument. But if you look back at that argument, it depended upon the conductivity being the same at all points on the surface of our Gaussian bag. But here now we've got a transition where we go from one conductivity to a different conductivity. So that sort of invalidates our old Gaussian bag argument, and we should reevaluate. So what we'll do is consider, instead of a bag, something more orderly, a Gaussian cylinder here aligned with the wire that crosses from one material to the other. And let's see here. So we'll have one cap that we'll call cap 2 with this surface area inside the less conductive material. The other cap, cap 1, over here on this side inside the good conducting material, and will be sort of enclosing a portion of this interface layer where the one material meets the other material. Okay, so material 1 with its conductivity and number density of free electrons, and material 2 with its number density of free electrons, conductivity, and field. Stronger field E2 than E1. So there's our setup. I'm just going to make a claim here that the charges that are responsible for this change in the field strength are going to be found at that interface. That there will be surface charge layers not on the outside of the wire, not at that outside surface, but at that internal interface. I'm going to claim that there will be a layer of excess positive charge with a surface charge density plus sigma located on that two-dimensional surface where the one medium meets the other. And I'll claim that there is going to be a surface charge layer with a negative surface charge density at the opposite interface layer over there. Since there has been a change in conductivity, that allows the possibility of excess charge inside that region where the material changes from the one conductivity to the other. So let's just verify that such an arrangement would produce the field we want. This layer of excess positive charge here would generate field to the right inside the resistive region. This layer of excess negative charge here would also generate field to the right inside that region. And outside that region, say over here, this layer of excess positive charge would be producing field to the right, and this layer of excess negative charge would be producing field to the left. So they could potentially cancel out here and cancel out over here, much like a parallel plate capacitor produces a uniform field between them, but no field outside of them. So some arrangement of positive charge and negative charge here and here at those interfaces looks like potentially it could produce the effect that we want, the stronger field in the more resistive region. But now let's try and prove it. Okay, so we're going to apply Gauss's law to our Gaussian cylinder here. So this open surface integral will replace with the sum of this closed surface integral for the flux will be replaced with the sum of two open surface integrals. So an open surface integral through cap 1 of E dot dA. And then plus the same thing through cap 2. and that'll have to be equal to the charge enclosed, if any, on this transitional layer where I'm claiming there is a surface charge density plus sigma. So sigma times, I'll write an A like this to represent an A like that, like a tall lowercase a, to represent the portion of the cross-sectional area of the wire that's intercepted by our Gaussian cylinder. So this A is the area of our cap. I guess a capital A would be the actual full cross-sectional area of the wire. All right, now at this moment, we have this unfortunate situation, this unfortunate notational situation where we've got two different sigmas meaning two different things. There are these sigmas are surface charge densities, and then there is these sigmas, sigma 1 and sigma 2, which are our conductivities. So a warning that we'll just have to use context to keep straight. Surface charge density from conductivity. So the green sigma will be our charge per unit area on this interface layer, and the black sigma 1 and sigma 2 will be the conductivities of the two materials. All right, so back to evaluating our fluxes. Let's see here at cap 1, we'll have dA pointing left, but the field coming into the right. They're opposite each other, so our dot product gives us a minus sign. So it'll be minus the field strength at cap 1, which would be the field in region 1, times the cross-sectional area of our Gaussian cylinder. And then at cap 2, here inside the more resistive region, we'll have the dA pointing right and E pointing right, so our dot product gives us a plus 1. So plus the field strength in region 2 times the cross-sectional area of our, or the area of our cap. And that equals the same thing on the right-hand side. At this point, we've got an area of our cap of the Gaussian cylinder that we can cross out. And we will now apply an earlier conclusion that in order to keep the current into that region equal to the current coming out of that region, we must have the same current density in both region 1 and region 2. And for the current density to be the same in both region 1 and region 2, then by Ohm's law, we must have the conductivity times the field in region 1 equal to the conductivity times the field in region 2. So what I'd like to do is use this expression to replace the field strength 2 with sigma 1 E1 divided by sigma 2. So that will look like this. First term is unchanged, minus the field strength in region 1, plus then sigma 1 over sigma 2 times the field strength in region 1 equals our same right-hand side. And we're going to then, oops, not quite the same right-hand side. We've canceled out that A by this point. So that equals that. And then if we finish solving for this surface charge density, we're going to try and determine if this is non-zero, if it exists. This then looks like epsilon naught times the field strength in region 1 times the quantity of the ratio of the conductivities minus 1. So examining what we have here, it looks like if the two materials were identical, so same conductivities, then this would be a 1 minus 1 would be 0, and there would be no layer. Okay, that's consistent with what we already know. if conductivity is uniform, then there should not be any surface charge layer inside the conductor. But if these two are different, and that is specifically if sigma 1 is greater than sigma 2, that is, if this conductivity is greater than that conductivity, then this is a number greater than 1. Minus 1 gives us a positive surface charge density at that transition. Therefore, we've got a positive charge layer here. If then we apply the same Gaussian argument over on this transition, in this case, we would have like sigma 1 would be this side and 2 would be that side. Anyway, if this ratio were less than 1, then we would get a negative surface charge density, which is what we have here at this surface. All right. So I'm claiming that we have proved then that we have a surface charge layers at these interfaces that generates the stronger electric field inside the region with the lower conductivity. So grand summary here of much of what we've discovered about moving from one conductive medium to another less conductive medium and back again. We have discussed our free body diagram. If we have, let's say, a driving force and a resistive force in region 1, that they're equal and opposite, we are in a sort of dynamic equilibrium in this region. We are also going to be in a dynamic equilibrium in the more resistive region, but in the more resistive region, the field strength is greater, so a stronger field produces a greater driving electric force, which is necessary because in the more resistive medium, the lower conductivity medium, we are going to get a greater resistive force. So we are still in dynamic equilibrium here in the more resistive medium. We just have a stronger field needed to oppose the greater resistive force in the less conductive medium. And back over here in region 1, we'd have, again, the weaker electric force is all that's needed to oppose a weaker resistive force. Okay, so that's our force scenario. And this is going to guarantee that we have the same current density in all three regions. Same current density, so that we have steady state flow. So that the current into the region equals the current out of the region, and we're not getting charge buildup inside the region. So those are all equal to each other. And lastly, our drift velocity. The drift velocity issue is a separate issue from the conductivity issue because the number density of free electrons is a separate property from the conductivity of the medium. But if, just for the sake of argument, let's say that the number density of free electrons in region 2 happen to be greater than the number density of free electrons in region 1, then we showed earlier that the drift velocity in region 2 would be correspondingly lower, or our drift speed would be corresponding lower in region 2 than in region 1. So the higher concentration of electrons in region 2 would be drifting at a lower speed to generate the same current that a low density of electrons moving at a high speed generates in the surrounding media.